I should have checked if my microphone's on. I think it is. Okay, so let's go through the first thing, right? Explain how the graph provides evidence for how we know the maximum number of electrons in the p sublevel is 6, right? Well, I don't think you were getting it while I was trying to explain it, but this graph shows the ionization energies. It tells us pretty much how much energy it takes to remove that electron, right? For the group for this element at this given element, right? We can tell here, right? And we know based on our electron configuration that group 6 should start on boron, right? It should start on boron. And we know that it should end at neon. Well, what do we know? We know that electron orbitals like being empty, half full, and or full, right? Anything that gets to those situations is favored, right? So, if we look at boron, right? Removing the electron from boron here is easier than removing the electron from beryllium. This relationship shows, this reduced energy cost to remove this electron shows that this orbital wants to be empty, right? That's what that shows. The reduction in energy, because we're going down on the ionization energy chart, that shows that it is easier that this orbital wants to be empty. So that shows that there's a bottom for this electron orbital, right? Now we go up 3. 1, 2, 3. Now what do orbitals like to be? They like to be half full, empty, or full, right? So we can tell that here, 3, well, that if the maximum number of electrons was 6, it should have going from 3 to 4, it should be easier to ionize the 4th electron and remove it from this anything with if the p orbital is 6, because it would make the orbital half full, and it is. So that's the second piece of proof that the number of electrons in this sublevel is 6. Now we go up to sodium, and sodium has an extremely low ionization energy. It's after the sixth element, right? We know that we've gone up 3 electrons, and that if we remove this, the difference is so stark that we can tell that at this endpoint, right, it is really preferable to remove an electron to go to this endpoint. And we know that there's 6 electrons in between here in the last most preferable endpoint, right? So we can tell that it wants to empty, it's really easy to remove this electron because it's a full electron orbital, right? That's why it's so easy. It's a full electron sublevel. And it's also a full energy shell, but that part is a bit less important. And by the same virtue, right, I was saying the 3 energy sublevel is lower in energy than the 3p energy sublevel. Well, we're just taking this entire energy sublevel, we're taking this energy sublevel in its totality. Based on the electron configuration, we know sodium and magnesium, both, their valence electron is the 3s valence electron. Now we can compare these ionization energies to the entire 3p's energy sublevel and tell that overall this is probably something like, that's why I was like, it's something like 4,000, and this is a very rough estimate, it could be quite a bit more, versus something along the lines of 1250. Very low. This is a significantly higher energy level in comparison to the 3s sublevel. To what I was saying about energy subshells and sublevels, right? So what causes, right? How this graph shows that this sublevel is lower in energy than 3D is pure ionization energy, and it's the same thing as with 3s and 3p, right? 3s, we can see that the overall ionization energy of the sublevel is lower than the ionization energy of the, what do you call it, of the 3p, right? That 4,000 to 1,200, 1,250, right? But, and you may be wondering why this is like this, right? It's two reasons. One, there's a lot less electrons inside this subshell, which means there's a lot less repulsion forces in the subshell. Also, it's closer to the nucleus. It's closer to the nucleus, right? So, the nucleus stabilizes these negative charges because they're attracted to the positive charge. And all the repulsion forces between the two are stabilized, and they're closer to the nucleus than this 3s. This 3p orbital. This is 3p. P has a lot more electrons for more repulsion, and it's a bit further away from the nucleus, which is why it's higher in energy than the 3s sublevel. Now, 4s is lower in energy than 3d. If I could show 3D, you could do the same direct comparison of energies. You can see that if we add up the overall energies for 3s, it would be higher than for 3p, it's higher than 3s. And for 4d, it's not 3d, it's not on the page. It would be higher than 4s's. And you may be wondering why that is as well. Well, 4s is further away from the nucleus than 3d, but 3d has so many more electrons in it that all the repulsion forces raise it in energy and put it above 4s. That's the reasoning, but you can tell from a graphical perspective what what 4s should be. 4s and 3b should be. And how do we do Hund's rule? Well, Hund's rule states, right, that electrons prefer to fill an orbital singly, rather than doubling up inside an orbital because of these repulsion forces between the two. And so we can see here, right, one electron fills, 2 electrons fill, 3 electrons fill, but there's a reduction between N and O, right? That would be where in the ionization energy. It's easier to remove an electron here than at oxygen than it is at nitrogen, and that's because of that repulsion effect in the orbitals. The lower the lower ionization energy is evidence of a repulsion effect in that orbital forming. All right. And we talked about how the graph of the second ionization energy would differ. It would differ in that these are going any difference where it would be traveling through subshell. So there's a difference here in traveling through subshell. Because it takes significantly more energy to remove from a filled subshell, or a filled energy shell, as we can see with neon. It takes a lot more energy to remove an electron from a filled energy shell. So this would be shifted over for second ionization energy, because neon's already ionized, so it would be more similar to fluorine. But sodium's already ionized to fluorine. But as it's harder to remove an electron from an already ionized atom. So it's already harder. So the whole graph would shift up. It would also shift, honestly, it would shift kind of back that way. Because potassium would be more chemically similar to argon at that point for removing an electron. And then argon would be in more of a position of calcium, where it's a bit easier to remove electron because you're not going across an energy subshell. You're not pulling from a full energy energy shell anymore. So that's what happened to that graph. The fourth ionization energy of vanadium is 4,600 kilojoules per mole. The fifth ionization energy is 6,280 kilojoules per mole. And the sixth is 12,400 kilojoules per mole. Why is this one higher than the second, the fourth? Well, as you go across the periodic table, right? Actually, no. As you, I said this before. Ionization energy. It's not based on the atomic. Well, it's kind of based on the atomic radii, but it's not. As you further ionize an element, you're stealing more and more electrons from an already positively charged ion. That positive charge helps the ion hold onto electrons, which is why it increases steadily the ionization energy, because there's more and more positive charge to hold onto each electron as you remove electrons. Now, the reason the sixth ionization energy is so high is because if you look at where vanadium is on the periodic table, its sixth ionization energy is going across an energy shell. You're trying to pull one electron out of a completely filled energy shell, and it's a positively charged ion already. So that's why there's such a big difference there. You're breaking open an energy shell that's very stable in comparison to the fourth and fifth ionization energies. And we will pause that there. Alright, so for the last little bit, I got a bit of stuff going on, so I'm going to try and make this quick. To calculate the ionization energy of the hydrogen, the first thing we have to do is, all you have to do is use speed of light, which is c equal to, not Planck's constant, but it's, the speed of light is equal to frequency, what do you call it? Frequency times wavelength, something like that. Yeah, it's frequency wavelength. Either way, you divide this by the wavelength we got to find the frequency. You then take the frequency you get to and then use Planck's constant. Use Planck's constant to find the energy. And the energy I found was 131.7 kilojoules per mole. So this calculation is pretty easy, and if you really wanted to, you could just use a calculator to do it online. But when you're asking, explain why the convergence line in the ultraviolet spectrum must be used to calculate the ionization energy rather than the convergence line in the visible spectrum, we can recall our diagram, right? Convergence lines are looking at a state close to ground, at your ground state. If you use the visible spectrum, you wouldn't be able to see the convergence line at all, because it's not in the visible spectrum. It's in the ultraviolet spectrum. So the reason why we use the UV spectrum to calculate the ionized energy rather than the visible is because you literally can't see it in the visible spectrum. The convergence line would be outside. The convergence line would be outside of the visible spectrum, and that's it. So have a nice day, and I hope this helps.